and one particular string in that diagram is colored red. Now if I introduce this kind of a kink to it, then the rest of the coloring are not going to change for the whole diagram. The same coloring will stay, and I'm just going to paint this new thing also as red. Right? If I do this, then the new diagram after making this thing is also colorable. Right? So it's fine. I can go backwards also. If I had this as a coloring, if this was red, then this is also red. Since there are two reds, this is supposed to be red. So the color coming in is the same as the color going out. And therefore, if I unkink it, then I just put in the same color. Right? So in both directions, if this side was colorable, that side is colorable. This side, the whole diagram is colorable. This one is colorable. The same kind of ideas work for the other ones as well. Suppose this was painted red and this was painted blue. If I slide one under the other, I can paint it by the third color. And I'm forced to paint it by the third color. There's no choice. Because these two are different colors, so this has to be the third color. And you can go backwards. If this crossing has all three colors, then that means this is red, this one is blue, this is the next color. So over here it's forced to be the original color again. Which means I can unslide it, I just extend it and make it red and blue. And similarly for the last one, if this was red and blue, then you can see that if this was the original coloring and I slide this across, the coloring property still stays. The actual coloring was blue over here, it became green, that doesn't matter. The fact that I could color it is all that matters. Okay? So because my coloring property does not change under these three moves, so therefore the property of being colorable does not depend on which diagram of the knot I choose. If one diagram is colorable, every diagram is colorable. Okay, so this is an important thing which came from a very simple theorem. Okay, so let's get that knot is x1 plus x3. Right, that's the equation that I got. Similarly over here I have an equation. So let's write down all the equations. This knot is n-colorable exactly when the following system of equations has a solution. So the first crossing gave me an equation of the kind 2 times x0 is x1 plus x3. Over here I got the equation 2 times x1 is x0 plus x2. Over here I have the equation 2 times x2 is x0 plus x3 and so on. Right, so at every crossing I had an equation, and the equation is made up of these xi's. Xi's are going to tell me which colors to put over there. Right, and the colors now are numbers. Colors can be 0 to n minus 1, any color. So I'm looking for some solution for this. The first rule says that it should be non-uniform, which means that all the colors should not be the same. Okay, so I should not have something which is all of them are the same number. That's not allowed. So I'm looking for a non-uniform solution to this system of equations now. And this is a system of equations where this equality is equality modulo n. So it's equality in this new arithmetic of numbers which take values from 0 to n minus 1 only. Okay, does everyone get this? Right, so using this idea of colorability, I know that all of them are actually different knots. Right, because if there was a movie going from here to here, then there is a sequence of Reitmeister moves. But for every Reitmeister move, colorability is preserved. If this is phi colorable, then at every stage in the movie it is phi colorable, and so therefore this should also be phi colorable. Right, so that's the idea. So using this idea of colorability, I can distinguish knots. I can tell if the two knots are the same or not. Okay. Okay, so now we have this notion of n-colorable. So now instead of just 2 buckets, I have infinitely many buckets to put my knots in. Right? Okay, let's look at more examples. So we have this notion of n-colorability. First, let's understand this connection of equations to understand when a knot is n-colorable. So I'm going to start using a little more mathematics now than what we just did till now. A little more math involved, not too much more. We want to solve this equation, right? If this equation has a solution, then the knot is phi colorable. Whatever it is, modulo n, it's n-colorable, right? For a figure 8. Now, one thing to note here is that we don't really care about exactly what the coloring is. All we care about is it colorable or not. Right? Different diagrams of the same knot will have different kinds of colorings, but we just care about is there any coloring at all. That's all we care about. So in this equation setting, all we care about is there a solution or not. That's what we care about. We don't care about exactly what the solution is. We're just saying is there a solution or not. Now over here, if you look at this matrix is particularly nice, right? Do you see some nice properties about this matrix? Yeah? Okay, so there is a lot of symmetry in this. Now the symmetry happens to be
all
because of
these
this
columns
particular
and
example I
rows
chose.
are
That may not be
choosing.
true in general. But there is something more that you can see apart from the symmetry.
Sum of
Right.
all columns and rows are
Exactly. If you
0.
add up the columns, it gives me 0. If you add up the rows, it also gives me 0. Right? And this is going to be true in general. You can show it's always going to be true for this kind of connection of equations. So if the sum of rows is giving me 0, then it means that if this equation has solution, this equation has solution, this equation has solution, then I just add it up and that means this equation also has a solution. So this last row is kind of redundant. It doesn't give me any new information at all. Right? That's the meaning of saying that the sum of rows is giving me 0. But the last row is kind of pointless. In fact, any one row is kind of pointless. What about the sum of columns? So over here, because the sum of columns is 0, it means that if I have some solution and I add 1 to all of them, then it's still going to give me a solution. Adding 1 to all of them is like adding the sum of these columns. Right? So if I add 1 to one particular solution, then it is still a solution. Right? So which means that I can keep adding 1 to one of the solutions and make one of them 0. One of the numbers I can make it 0. Which means that I can drop one of the columns. Because if that number is 0, then that column plays no role at all. The last column in this case. So this particular matrix has a solution if and only if I remove a row and I remove a column and this set of equations still has a solution. Okay, so that's what we are going to do. From this matrix AK, this one has a non-uniform solution modulo n. Exactly when the matrix obtained from this by dropping a column and dropping a row still has a non-zero solution modulo n. Okay, so might as well drop a row and drop a column and then work with this new system of equations instead. Right? Okay, so now we are going to work with this new system of equations where you are dropping a row, dropping a column, and all I care about is whether it has a non-zero solution or not. Now suppose I give you a matrix equation of this kind, some matrix into x equal to 0, not modulo 0, but it's actually equal to 0. In that case, if you've done a course in linear algebra, I'm saying that this matrix A times x equals 0, when does that system of equations have a solution? So what do you think? When should it have a solution? Determinant of A is non-zero. Right? So if the determinant is non-zero, it has an inverse, you can multiply it, and then if it's non-zero, then the only solution